I will continue with the story about human longevity, and I will particularly focus on one phenotype, which is glucose regulation. And I will present some data from the night longevity study, which has already been introduced by Rudy Westergaard. So what we did is actually researched in all of the Netherlands for people that were, so we addressed actually all the municipalities for people who were above 90 years of age. And we also asked for the date, the names and the birth dates and the dates of death of their parents. So we could link them on having common parents. And in this way actually we identified people who did not only become very old themselves, but who also had a brother or sister still alive who was also very old. So these are called the nonagenarian siblings, and actually from the whole of the Netherlands we identified only 421 families, which shows that this is an exceptional phenotype to be both alive. But the idea was also that if you want to become long-lived, there is actually three main reasons. It could be chance, it could be environment, or it could be genes, or any combination of those three main factors, right? And since we were really interested in genes, we chose for this genetic approach to go for people who had a brother or sister alive. And the idea was then, well, if it's genetic, then it should be inherited to their offspring. So we also included the children of these long-lived people. And as a control group, to as much as possible reduce the impact of environments, we choose the current living partners of the offspring. So this is, let's say, the design, and a lot of our work over the last years has been done by comparing these offspring of long-lived siblings with their current living partners. Well, this is just an example of such an exceptional family. In this case, there were not only 2 people who became long-lived, but actually 5 of them. Family Lucassen. And well, as a first thing that we did is to prove that our recruitment algorithm was successful. We looked at we compared the mortality of these people and all first-degree relatives with the mortality of their respective birth cohorts. And we saw that actually all first-degree relatives of the programmed siblings, so either additional brothers or sisters or their offspring or their parents, had an about 30% lower mortality risk compared to their respective birth cohorts, while the living partners of the nonagenarian siblings did not have this, indicating that indeed we have enriched for familial longevity. Well, if we start now comparing the offspring generation with the partners, it's difficult at this stage to look at that, because luckily not many of them have died. They are approximately 65 years of age by now, but we can look at the prevalence of major diseases, which is what we did. And there we see that if we compare the offspring with the partners, that if we look at the percentages, which are in brackets, is that they do have a lower prevalence of myocardial infarctions, like 2.4% versus 4.1%. They also have lower prevalence of hypertension, and which is particularly striking, they have almost half as much type 2 diabetes. And this was one of the reasons which led us to study in more detail their glucose metabolism. And to study glucose metabolism, you can do it in many different ways. You could look at, let's say, a very huge group in which we just take, let's say, a random measurement, which is what we did here. We used the full cohort, which is about, if you exclude diabetics, it's about 1,800 people, and with the diabetics included, it's about 2,500 people. And we just look at whether glucose taken at a random moment at the day, irrespective of whether they had just eaten or not, was different between the groups. And what we then see is that indeed, if we compare offspring with partners over all the age categories, glucose is lower in the offspring group. And actually this difference remains after we have excluded the subject which type 2 diabetics, which was more prevalent in the partner group. Well, then of course we can zoom into glucose regulation. So going from 1,000 people, we now go to hundreds of people, and we invited them to come fasted to our research center, and we gave them an oral glucose tolerance test. So we let people drink 75 grams of glucose, and then we took blood samples at just before they swallowed the glucose drink, at 30 minutes, 60 minutes, and after 2 hours. And we measured in these blood samples the insulin and glucose trajectories. And what we then saw is that we already saw differences in fasted glucose and insulin, but if we look at the trajectories, we could see that the insulin trajectory was not really different, but the glucose trajectory was different. So it did not reach as high a peak, and the return to normal was faster. So if you would calculate the area of this curve, it would be significantly reduced in the offspring group, which would indicate that with the same amount of insulin, they are better able to clear the glucose from their blood, which might indicate that they are more sensitive to insulin. So what we then did is to again zoom into a 10-fold lower group, and now we are looking at tens of people. So actually we looked at 12 offspring and 12 partners, and we invited them to the research center for half a day, where we actually tested the insulin sensitivity with the gold standard method, which is the hyperinsulinemic clamp method. And with this we can actually address the question whether they differ in insulin sensitivity, and also whether this difference is most pronounced at the level of the peripheral tissues, like muscle and adipose tissue, or at the level of the liver. And well, because we have such a small group, it now becomes more important to really match offspring and partner for confounders. So it was really important that they had a similar BMI, that they had similar levels of exercise, etc. So we took very much care about this. And this is then how the glucose clamp study works. So to briefly explain you what is happening, this is the blood glucose, and this is what we clamped. So we clamped it at a strict value of 5.5. And the idea is then that if you would give insulin, biologically the effect of insulin is that it is normally produced after a meal in response to carbohydrate-rich foods, and it signals the body that there's plenty of glucose present. So normally the body would then preferentially dispose of the glucose to the peripheral tissues, which then instead of using fatty acid oxidation, they switch to the use of glucose as a fuel, right? So you get an enhanced glucose disposal to the peripheral tissues. And because normally it's a signal that there is plenty of glucose around, it's not necessary for the body to make its own glucose. So normally in physiology, insulin suppresses the endogenous glucose production by the liver, right? So that these are the two effects. Well, what we now did, so in general what would happen if you would give people insulin is that the blood glucose levels would lower because the endogenous production is reduced and you do dispose glucose. But you want to prevent blood glucose from lowering because we do not want people to enter into a hypoglycemia. We clamp the glucose levels and we actually supplement glucose to really make sure that glucose levels keep stable. And then the idea is the more sensitive you are to insulin, the more your glucose levels in blood would have dropped, so the more glucose you have to give to compensate for this decrease, right? So insulin sensitivity is then measured by the glucose infusion rate. The more glucose you have to infuse, the more insulin sensitive a person was. And well, maybe, which is important for the rest of my talk, this is a rather invasive procedure because people have actually IV cannulas on both arms. One arm to administer the insulin and the other arm to take repetitive blood samples to really make sure it's a kind of titration experiment that always you keep your glucose levels at 5.5. So it was quite an endeavor for people to come. And this is then the end result. So we actually took two different doses of insulin, a lower dose and a high dose of 10 versus 40 international units. And here you can see how the glucose infusion rate changes in response to the insulin infusion. So with the low insulin dose, we do not see any differences between offspring and partners, while with the higher dose, we see that we need to compensate more in the offspring group with giving them extra glucose to keep this glucose level stable. And these are then the glucose trajectories throughout the clamp. So you can see that between groups, they are kept at a similar level, but that we need more glucose in the offspring group to keep them at that level, indicating that they are more insulin sensitive. And if we would then go to the data which based on stable isotopes, we can discriminate whether the insulin sensitivity is preferentially in the peripheral tissues or in the liver. we saw that it is mainly this glucose disposal rate which is enhanced in the offspring. It's about 25%, which is quite a big difference. And we didn't see any effects in the liver under these conditions. Now, what is also good to note is that we asked the age of death of the, well, both of the offspring and of the parents, and if we plot actually the age of the oldest parent or the mean age of the parents with glucose disposal, we see actually that there is a positive correlation, which means what you see already here is that the grey dots are the offspring group, and they have, of course, parents who became older because that's how we selected them. But even if you would do this in the partner group only, there would be this positive trend, indicating that it's not something peculiar for these families, but that it may be something which could be applicable to, actually to the rest of the society. And this is in line with what others have found, because this is some older data from Gerald Reven, where he showed that if you would look at middle-aged people and you would actually categorize them dependent on their insulin sensitivity, that it is the group who is most insulin resistant who develops all types of age-related diseases, so not only the type 2 diabetes, but also cancer, hypertension, and that there may actually be, you know, a common cause. It's not restricted to elevated risk for type 2 diabetes. This is actually exactly what I showed you in my previous slide, that also in the offspring group, these diseases are less prevalent. Well, as I said, it is a rather invasive procedure, and it's difficult to implement this, you know, to a larger group of people. So we have been looking over the last years whether we could find systems that are less invasive and that could also yield valuable information about glucose regulation. Well, and one of the systems that we have been experimenting with is a so-called continuous glucose monitor, which is a device which is inserted into the belly. It's actually minimally invasive. It's a small capillary which samples glucose from the interstitial fluid, and you can actually, in a minimal invasive way, you can get a huge amount of data because you get measurements every 5 minutes, meaning you have 288 measurements per 24 hours. So, you know, and you can let people wear this for 3, 5, 7 days, yielding a lot of information. And well, actually, we were interested in testing this also in the offspring partner. And for this, we took a very small sample because it was a pilot experiment. So we took, in total, we looked at 37 people that were about the same age as the offspring, so around 60 years of age. We had 26 offspring people, and we also took young people. So the slide which I will show you is actually the average in glucose trajectories for these 3 groups. Young people compared to people who are older in chronological age, and then between people who have the same age, I'm going to compare the glucose trajectories of the ones who are derived from these special families to their partners. So, and this looks like this. So the first slide is to compare young and old, and what you see is, so here is depicted time, and these are 3 consecutive days and nights. So what we see is that glucose levels are lower in the night, which is what you expect, and then they are much higher during the day, and they increase, let's say, around these moments that people normally have their meals. So we see nice excursions, lower in the night, and then we see changes during the day. We see fluctuations. Now, if you look at what happens when people become older, it's striking that everything is higher. So on average, glucose levels throughout the period are higher, right? Indicated by the red line. And also the fluctuation in response to everyday challenges are also more pronounced. However, if we now look then within the elderly, and we start to compare people from long-lived families with their partners, we actually see that during the day there are not that many differences. Maybe if you would have a larger group, we could have identified the same differences that we saw previously with the oral glucose tolerance test. But those differences that we saw with the oral glucose tolerance test may just be the tip of the iceberg. Because if we now start looking at the night, these people are like the young ones. They are like people, their glucose excursions are similar to those of students of 25 years of age on average. So this is a very striking finding. And we are at the moment further exploring this finding by enlarging the group size. And by, first of all, it opens up two possibilities. First of all, we really would like to know what is behind it. So what is the biology behind these different glucose trajectories, and also it could be a way, it could be one of the endpoints that could be tested in several trials which relate, for example, effects of exercise or food intake. And well, I'm also myself involved in a European project called Switchbox, in which we are really interested also in the role of the brain on these glucose trajectories, because it is known that, for example, insulin, which is normally formed after a meal, it is not only affecting the peripheral tissues, like the muscle, the liver, the adipose tissue, but there's actually also an active transport system which transports insulin into the brain. And from within the brain, it actually potentiates some of the insulin axis in the periphery. And there's also very nice data from model organisms that, for example, if you would remove the nervus vagus, that actually insulin in the periphery is only half as capable as normal to inhibit endogenous glucose production. So it looks like, the brain is one of the organs which is in charge of maybe of some aspects of these rhythms that cannot be explained by food, for example, these glucose levels at night. And within Switchbox, we are now really trying to recruit people from the long-lived families, the offspring and their partners, to better understand how the brain might influence these glucose trajectories. So we are collecting lots of other physiological parameters like continuous ECGs. We are looking at core body temperature continuously also. We are collecting blood again to do repetitive blood sampling to really look at the circadian profile of the major endocrine axis, like the thyroid hormone axis, but also the HPA axis, to see if this can somehow explain the differences. And we will also play around by modifying how the brain reacts by giving people insulin. Because if you give insulin via the nose, it specifically interferes with actually the insulin axis in the brain, and we would also like to test how these may impact various aspects of these rhythms. So I guess that I can conclude that with all the different means that we tried, is that we found striking differences in glucose metabolism to be associated with familial longevity, both the standard ways like oral glucose tolerance test, hyperinsulinemic clamps, but also with these novel devices. And that this is an area that we are going to pursue further, particularly paying attention to the role of the brain. And these are then the collaborators that I would like to thank from the departments of gerontology and geriatrics, molecular epidemiology, Department of endocrinology and radiology, with whom we also formed the Switchbox consortium. So thank you for your attention.